You have the triangular arrangement of wires, something like this in 3 dimensions. But we're just going to look edge on to the triangular arrangement where the 3 wires are going into the page. You have 2, I've labeled these wires 1, 2, and 3. Of course, we know that I3 equals I2. We're told that in the problem. I put that down here. And we're going to try to find I2. We also know that I2 and I3 are into the page, whereas I1 is out of the page. And so in this arrangement, the forces on wire 1 from wire 2 and wire 3, which we can consider wire 2 and wire 3 fixed. So the forces are opposing the force of gravity, and I1's just floating there on top. So what we need to find I2 that can make all this happen. All right, so the first thing I think would do is find the magnitude of the force on wire 1 from wire 2, and we can relate that to wire 3 as well. So let's get an idea of what's going on. Actually, as an aside, let's just remember that if we have some wire with some current, I'll call this I2 just to keep keep everything. Actually, I'll make it go downward, just to keep everything consistent with the problem. I'll call it I2, and then we have some other wire over here with the current I1 going up. What we can think about is the field that I2 creates. Remember the second right-hand rule: point your thumb in the direction of the current and your fingers curl in the direction of the magnetic field. So that means over here, the magnetic field due to wire 2, I'll call that B2, is into the plane. And on the other side, when your fingers curl around to the other side, B2 over here is out of the plane. So it's going to circle around like this. So if we want to find the force on this wire from the field set up by this, well, it's the same thing as from the previous chapter where we look at the Lorentzian force on wire 1, QV cross B2, but of course we're dealing with wires and currents. The magnetic force on wire 1 is equal to IL cross B2. So wire 2 sets up B2, and then wire 1 that's running in that field feels that force. What is the direction of the force? Well, goes back to right-hand rule number 1, which is the rule of cross products, which means you point your finger in the direction of IL. So the current's going upwards. So IL is in this direction. You curl your fingers in the direction of the second thing in the cross product, which in this case is, the field is into the page. So I'm going to point my fingers in the direction of IL, curl my fingers in the direction of B2, which is downward into the board, and the force is that direction. Now, of course, this wire is going to feel a force also in the other direction, but we're not going to worry about that right now because in our situation, we're just worried about the force on this wire 1. Okay, so back to the problem at hand. If I want to just look at the situation, the orientation that we have it, so I'm going to box this off so it doesn't get in the way. I'm going to look at, this is wire 1, this is wire 2, and I'm going to label this I2 into the page, I1 out of the page. Well, I2 is setting up a magnetic field that, according to the second right-hand rule, thumb in the direction of the current, which is downward, fingers curl in the direction of the magnetic field. So B2 is going to be in that direction. But we also know that it circles everywhere, and the magnitude drops off with r squared, but nonetheless, the magnetic field always, everywhere, is circling around, and that means even all the way out here where I1 is, it's circling around. And of course, just to save paper, I'm not going to draw the full circle, but you get the point. So that means that this magnetic field, B2, points at this one location tangentially to that circle. If you remember when we had centripetal motion and something spinning around in a circle, we could say at any one point its velocity was tangential to the circle. Well, the same thing is true here. At any one point where, like this one point where the wire is, the magnetic field due to wire 2 is tangential. So, what is that B2? Well, we know the separation between these two wires is, sometimes we'll call it R, but in this case we're given in terms of A. So B2 then, and we've already derived this equation, so we can start with that. Mu naught I2 over 2 pi R, or in this case the separation is A. That means at distance A, the magnitude of B2 is thusly. What is the orientation? Like, what is the angle between B2 and A? Well, it's going to be 90 degrees, right? Because it's tangential to the circle, so that means it must be perpendicular. So what is the force on I1 from B2, which is created by I2? The force, actually I'm going to call it force 2, because just remember, everything is in relation to this one wire. So the force of B2 on wire 1, or I'll call it F2, is equal to IL cross B2. And this is going to be I1, because that's the current traveling through the magnetic field. This is the length of the wire, which is the same as all of them. I mean, you can label it 1 if you want to, but they're all the same length. So current I1 traveling through the magnetic field set up by B2. What is the direction of that? Okay, well, right-hand rule number 1. Right-hand rule of cross products. Point your fingers in the direction of the current, which is kind of hard to do on the camera here, which is out of the page. Point it in the direction of the magnetic field, which is tangential to the circle. So the force points this direction. Which this is what we talked about in class. When you have two wires with currents in opposite direction, they repel each other. So that line of force goes directly along the line of separation between the two wires. So there's a 90-degree angle here, and there's a 90-degree angle here. Okay, let's just, for the time being, let's just give the magnitude. And we'll come back to the orientation because we have to talk about the angles and stuff in a second anyways. But if we just want to deal with the magnitude, we know it's I1 L B2. We could say sine of alpha. I guess we're not using a phi anywhere in this problem, so I'll just say sine of phi, where phi is the angle between I1L and B. That's 90 degrees, right? Because the current is coming up out of the page and the magnetic field is tangential to the circle. So that's just 1, and this is I1L B2. What is B2? We found it up here. B2 is the field set up by this wire. So F2 equals I1L times mu naught I2 over 2 pi A. I could clean that up a little bit, put it in an order I like better. I'll say mu naught I1 I2 over 2 pi A. So that's important. We need that magnitude of the force. Well, now we also have to say what is F3. Remember, F3 is the force from this wire over here. Well, it's all going to, going to follow the same thing, and we know I3 is equal to I2, so F3 must just equal F2 u naught I1 I2 over 2 pi A. Again, that's because I2 equals I3. You would do the same thing over again, but you deal with the wire over here. The currents in I2 and I3 are the same, so that means the force on wire 1 is equal. Just put a little box around there. Okay, so now that we have the magnitude of this force, it's just like any other addition of forces problems that we've worked, like maybe in Physics 1 or something. We're going to look at wire 1. We have wire 3, wire 2 down here. We already showed that the direction of the magnetic field, I'll draw it real lightly because I'll erase it in a second. The direction of magnetic field from wire 2 is in that direction. It's tangential to the circle, correct? I'm just redrawing the situation. Now we have to look at this guy, and we know just like this one, whose magnetic field is circling in that direction, well, the current here is in the same direction, so it's going to circle in the same manner, but because wire 1 is on the right side of wire 3, when you draw that circle around, at this point, B3 is in that direction. We also know that F2 is perpendicular to B2. So we drew this up here already. All right. And we know the exact same thing is going to happen in here. The force is going to be perpendicular to B3. I'm going to erase the magnetic field from wire 2 for a second. We're done with that. So now the force from the field set up by wire 3, we call that B3, is going to be perpendicular in this direction. So both of these wires are pushing wire 1 away in a direct line path. And of course, this is the triangle. So I'm going to erase the magnetic field due to 3 for clarity. Now we have one more force that we've been kind of ignoring thus far, is we know that there is a gravitational force pulling this wire down. I'm calling that Fg. What else do we know? Well, this is an equilateral triangle, so theta equals pi over 3, 60 degrees. I can even put that over here in my nose. And I can say equals 60 degrees. That's just because it's an equilateral triangle. Now these are two, I forget what the geometric term is for this angle and that angle and how they relate, but this must be theta and that must be theta as well, just by properties of geometry. You know, if I take two lines and I draw two straight lines and draw one straight line through them, then this angle theta equals that angle theta. So anytime you're adding forces, it's always best to draw a free body diagram. X, Y, you have F3, F2, Fg, these are both at angle theta. I can draw the free body diagram again and say F3y equals F3, in this case, sine of theta. And I can say F2y equals F2 sine of theta. I'm cramming a lot on this diagram. I probably should have done that. This is Fg. F3x equals F3 cosine of theta, and I'll put negative F2x equals negative F2 cosine of theta. I put the negative in there because it's in the negative direction. Now you could do this in unit vector notation. It seems like people tend to understand it a little more clearly if I do this little box routine that I usually do. So F2 has the component of, in the x direction, negative F2x equals negative F2 cosine of theta. And remember, we already found the magnitude of F2. I'm leaving it out for now, just for clarity. And F2 in the y direction equals F2 sine of theta. Well, F3 in the x direction is just F3x equals F3 cosine of x. And in the y direction, F3y equals F3 sine of theta. And, yeah, no, I'll leave it there. We know that F3 equals F2. I'll show you that in a second. The force of gravity has no component in the x direction and has component negative mg in the y direction. Okay, so if I sum up all my forces in the x direction, I get negative F2 cosine of theta plus F3 cosine of theta. Whenever you sum up the forces, that always equals mass times acceleration by Newton's second law. This is in the x direction, so it's max, but nothing's moving. It's just held there in equilibrium, so it equals 0. So F2 cosine theta equals F3 cosine of theta. Cosine theta cancels, so F2 equals F3. And we already knew that, but it's nice to prove it, right? So to continue on, let's see, I can do this. The sum of the forces in the y direction is F2 sine of theta plus F3 sine of theta minus mg equals may, and we know it's in equilibrium, nothing's moving, so that equals 0. So move this out of the way now. So F2 plus F3, I'm just simplifying this, sine of theta, I'm factoring out sine of theta from each side, equals mg. But we know that F2 equals F3, so this is just 2F2 sine theta equals mg. Solve for F2. Mg over 2 sine of theta. Okay, so where now? Where to now? Well, we have to go back to what we saw before, and we have to plug this into F2. So mu naught I1 I2 over 2 pi a equals mg over 2 sine of theta. Well, you see the 2's cancel out. Also, we know that sine, this is a nice angle, sine of pi over 3 equals square root of 3 over 2. We can plug that in. So we're solving for this guy, I2, 2 equals mg pi a over mu naught I1 sine of theta. I'm going to rearrange things. I'm also going to plug in the square root of 3 over 2. So I2 equals 2 pi over square root of 3. I'm just pulling all the constants to one side to make things a little cleaner. Times mga over mu naught I1. Of course, g and mu naught are constants too, but they're a little bit more complicated than just a pure number like 2 pi and square root of 3. So that's why I pull everything out like that. Oh gosh. Did I forget L? Way back here, I forgot L. Means L must come into play here. Here. And here. And once you plug in all the numbers, you get I2 equals 113 amps.